So here is the plan for day 15. We're going to do a review of interval notation. I know sometimes this is a topic that is actually is very easy, but the notation sometimes throws us off. So we're going to do a review of that. Then we're going to do the anatomy of a rational function. We're going to do you guys are going to analyze a rational function and look at all the key features of a rational function on our Jamboards that I think has been a good addition to what we've been doing. We're going to talk maybe a little bit about the algebraic. We're going to make that connection of the features, the way we find the features geographically to the way we find the features algebraically. So we're going to make that, and we may go back to this next class too. Now we're going to talk a little bit about a new type of rational function that is connected to our next assignment, which is Desmos Rational Investigation 3. So I'm going to introduce it. I know most of you are working on the investigation 2, the reciprocal of quadratics, and I gave feedback, I believe, to everybody on different screens. Different people are in different places, but we're making progress. And as always, I'll hang around for a little bit after for Q&A. I don't think I put this in the plan for today, but nonetheless, that's what we're doing. All right. So let's postpone it for immediately. And this is what we are going to do about interval notation. Okay. So an interval, we can think about it as a set of points. A set of points in a specific case that we're looking at that describe a certain space. And the way we describe this space is with these different types of notation. If this is new to some of you, and as I'm going along, something doesn't make sense, please unmute yourself and say, Mr. Garcia, can we go back or whatever, please. If not, I keep going. So we have here a number line, and we're going to illustrate this number line, and we're going to use notation for intervals. So there are two types of intervals, one that we call open intervals. And these intervals do not include the end points. And let's talk about what the endpoints are. So let's look at the very first one here. X is greater than -3, okay? That means that this interval, this set of points, is any number that is greater than -3. So for example, -2, or 1, or 0, or a -2.999. So this is our interval, yeah? Now you see kind of a red line, any number greater than 3. However, the part that is open is, notice this notation that is what we call strictly greater than. In other words, this interval does not include the number 3. And if I look here, you're all going to see the second coordinate be 1. Don't worry about that, disregard it. But take a look at this. I'm at -2, at -1. But when I come here, it tells me, hey, this is undefined, because the interval does not include that number. It's an open interval. That's what it means. So we can write it like you see here. X is greater than -3. The notation that you see underneath is the same thing, except that we just said -3 is smaller than X. They represent the same thing. In other words, here we're saying any number greater than -3, and here we're saying X is any number that is greater than -3. And if you see, when I click on this one, well, we get the same interval, right? They overlap. Usually, we use the first notation for these type of intervals, okay? But the second one is not incorrect. But this is, the first notation is the one that is more commonplace when we indicate an interval where the numbers are greater than something, okay? The second type of notation that you see here in the third row is this, is brackets that are open brackets, and it's 3 comma infinity. And actually I could do here a positive infinity. Yes. So this notation tells me that I'm taking a set of numbers beginning with 3 but not touching it and going all the way to positive infinity. Basically the same thing. Yes, we're just writing it differently. Yeah. So this notation is the one that we use more common. Don't ignore the bracket, the curly brackets. That's a Desmos thing, and I discovered it today, so I was playing with it, and I figure this would be a good visual to illustrate it. So you would usually write x greater than -3. You can write the second one, but usually we use the first one. Or you can write this from -3 to positive infinity, the same identical idea. Yeah. Okay. Now
Excuse
here's
me.
another example. Yes.
Yeah, can I ask a question? So that third one that you just did, it looks offhand, like initially it looks like an ordered pair to me,
It does look. Yeah, it's
but we
not an
can't.
order paired. It's not an.
Okay.
That's a great question,
Oh, because we're just
Suzanne.
graphing on a horizontal line.
Yeah, no, yeah, that's an excellent question.
Okay.
If you notice, when I click on it, we won't see it. It's a point somewhere. But in the way we're approaching this, don't think of it as an order pair. It is an interval. Yeah,
Okay.
in this case, that's a great observation. When we're talking intervals, the brackets that are open denote open interval. In other words, it doesn't touch the endpoints, but it's not an ordered pair. Thank you so much for that, Suzanne. Good. Now, there's another example here. Sorry, I'm making that. Okay. And this next example is x, any number. Basically, you can look at it like this. X being any number smaller than 2, right? So if you can think a moment to visualize what that might be, any number smaller than 2. So it could be 1, it could be 0, anything this way, right? So it would look like this. Yeah. And it will go all the way to negative infinity. Yeah. So, and the same thing as the above, x smaller than 2 is the notation that we normally use. Okay. So we put the x first. If I look again at the first example, is any number greater than -3. If I look at this example, I can read it as any number smaller than 2. And the notation underneath, similarly to above, is not incorrect. It's just not as commonly used, right? In other words, we're saying here 2 is greater than any number, which is, yeah, 2 is greater than anything that we have on that interval. And if I click on it, you'll see that it represents the same thing. So both notations are correct. Normally, we use the first one more often. And then the equivalent of it underneath is this interval notation. Again, not an order pair, an interval that goes from negative infinity to 2. What I do want to highlight here in this notation and this notation of the brackets is this. We always put this, imagine that this is on the number line, and the number that we put on the left is always the smaller number on the interval. Yes, so in the first example here, 3 is the smallest number in the interval, and then we go to the right? Here, the smallest number in the interval is negative infinity. We're beginning at negative infinity. So think of the interval in this notation as the start value and the end value for that set of points. Okay, so we have intervals that go to infinity one way, to infinity the other way, to infinity and beyond, right? Now, we also have these intervals that are smaller, right? These, so an interval like you see in the next example, that is an interval, the way I would read it is this: any number between -3 and 4. So in other words, I could be at 0, and that's part of it's in the interval. But if I go to -4, that number is not on the interval. Or if I go at 5, that number is not on my interval. So this represents just this section, yeah, that chunk of my number line. And it does not include either the -3 or the 4. Yeah, it's an open interval. So, and the notation underneath, see, if I had put there a notation for numbers for decimals, it would have put an ordered pair, and I didn't want an ordered pair. So it's like a note. So the notation that we use is this one, -3, 4. And these two, if you see, we always place the smaller number first, the initial value, as it were, and then the bigger value, right? So these are open intervals. This notation and this notation are equivalent. So you can write either of them, and both are fine, both are perfect. And so you might be asked to do some of these in some of these decimals that are upcoming, but now you kind of understand. All right, so that's open intervals. The other type of interval is a closed interval. And the difference is very simple. An open interval does not include the endpoints. A closed interval does. Okay, and so let's look at, let me erase this friend. Okay, so let's look at our first example, and the difference is very evident in this notation. Take a look at this. We use the greater or equal sign. Greater or equal. In the open interval, we just use the greater or smaller, strictly greater or strictly smaller. This one is greater or equal to, or smaller or equal to. Yeah. So if I read this, I would read it like this: any number that is greater or equal to -4. In other words, my interval includes the 4. Yeah. It does not include 4.0000001, but it includes 4 and onward. Yeah. And I know that because of the greater or equal sign. And the same stuff as before. The second notation, again, is not incorrect, but is less common. So I encourage you to use this one. The first one is the most popular in mathematical circles, although, again, the second one is not incorrect. Yeah, represent the same thing. Cool. And then the bracket notation, take a look at this one. Actually, technically, this is not strictly a closed interval, yes? Because it's closed on the small side, on the left side, because it includes a -4. But infinity is an amazing concept. There's no such number. There's no place that we go, oh, here's infinity, and we stop, right? It's unlimited. So any interval that includes infinity, of course, it will be open on that end because we cannot reach infinity. So notice that the bracket on the left side is a square bracket. That tells me that is closed on that side, okay? Similarly, this interval now tells me I'm looking at any number that is smaller or equal to 5. So 5 could be in my interval, or anything that is smaller than it. So something like that. Yeah. So 5 is in the interval, see? And then anything smaller, but of course, anything beyond 5, greater than 5 is excluded. Yeah. Similarly, the same notation underneath. That is correct, but less common. We always try to put the x first. So all the set of numbers that are smaller or equal to 5. And then the second, the other notation, which is the bracket notation, notice that we begin at -infinity. And of course, that has to be open to 5, and the 5 is closed. Okay, cool. And then the last example is this one, that this one is a strictly closed interval. Yes, it includes the -2 because we have smaller or equal, and includes the 4.5. The notation is with the square brackets at both ends, and this is the interval that we would see on our number line. And sometimes we literally draw, I'm going to show you what we do on a number line. We do something like this. We do something like this on a number line, which is perfectly fine. we do something like this and something like this. Yeah, and that tells me that interval is from -2 to 4.5, and it's a closed interval. Yes. We also do one more notation, and that is on the number line as well. And I'm going to show you what that looks like now that we get the idea of the open and closed intervals. Let's stay with this interval, and we can represent it on our number line this way. Let's say our interval was closed. We do this, we put a dot here, and we fill it in. And we do our line here as straight as I can make it with my mouse, and do these and fill the dots in. So if the dots are filled in, the interval is closed. If the dots are not filled in, I could have, for example, this interval, I'm going to stop at 3, would be open. It would be the equivalent of this, -2 between 2 and 3. Yeah, between 2 and 3, it's open. And if I change this and I fill it in, then my interval would become this. Yeah, great, smaller or equal to. And of course, my other notation would be this. And these would be open, and these would be closed. Yeah, so we have 3 forms of notation. The typical greater or equal or greater than, strictly the symbols, greater, equals, etc. So which is 1. The brackets, and this number line illustration with the circles open or close, illustrating the interval. Okay, so I hope this, for some of you who already knew it, was a review. And I hope that for those of you who didn't know it, it's clear. Again, if you have questions, you can ask me. You can ask me now. And I know some of you are a little shy and you ask me after, but that's okay. All right. So now we're going to go. Are there any questions? No? No. Thank you. Okay. So I'm going to go back. Now we're going to go to our homepage. And let me see. Let me refresh. Okay, we have, don't go to the Jamboard, please. Don't go, because I know you guys are Speedy Gonzalez. First, we have to make our teams and all that jazz. But let me tell you about this Jamboard, okay? Be patient with me, friends. So here it is. It's very elegant. I made it with a black background and stuff. So here is the task that you and your partner will be collaborating with. The question is, how do we determine? Don't do any answers, people, not right now, because you don't have your partner. You don't know where you're going, okay? Okay, so the question is, how do we determine? We have here a rational function. We've been playing with some of these. And how do we, I only want you to look at graphically. I mean, some of you, I know you're going to give me some algebraic stuff. That's okay. But how do let's pretend that you're explaining to somebody who doesn't know, how do you determine the vertical asymptote? And feel free to sketch them, of course, right? How do you determine the horizontal asymptote? So you can actually put me a little sticky and say how you do that, right? Yeah. So you can come here and say, this is how we do the vertical asymptote or the horizontal asymptote. How do we determine the domain? How do we determine the range of these specific rational function? How do we find the x and y intercepts? Where are the positive and negative intervals for these function? Be careful with this question. I don't want to give it away, but one thing is positive and negative, and another one is intervals of increase and decrease. Watch out, because that is an easy mistake to make. So then, of course, I didn't put the teams. I just realized that. However, if you look at the top here, you see 1 of 15. Yeah, and then if you go 2 of 15, 3 of 15, and so on and so forth, you know that this number here is your group number, okay? And given that you guys are so smart, then I'm not going to of your team and your teammate. I'm going to count from 3 down, and then I'm going to show people who may not know how to get to the Jamboard. Remember, everybody can work on anybody, but you guys are being good citizens and you're not doing anything foolish, okay? I've been bragging about you right, left, and center, so don't let me down. Okay, so 3, 2, 1. Okay, so those of you who are not sure, if you go to our homepage in D2L, here's the Jamboard link. Yeah, here, and that will take you there. A lot of you already landed there. And okay, so what we're going to do is we're going to literally do the anatomy of this thing. Can everybody see the Jamboard? Nolua, thank you. Okay, just well, I always need to be checking because, okay, so group 9. So we're going to be just looking at one item at a time. Okay, so do you want to tell us about the vertical asymptote, please, group 9?
So I said define the vertical. Oh, I think it just glitched for me.
No, sorry. Go ahead, Justin.
Okay, so I said define the vertical asymptote. You look at the graph and determine which point the graph doesn't touch on the x-axis.
Which point the graph doesn't touch on the x-axis? Okay. Yeah. Well, if you look at it this way, if I look at the graph, it touches the x-axis here.
Yeah, by that I meant like where it doesn't touch for like the points of x, I guess. Kind of.
I see. Okay, this is yeah, it's not an easy description. Okay, yeah. Let's go to group 10, see what they said for the same question. Group 10, can you, I'm going to make these a wee bit bigger. Can you tell us a little bit about these, please?
So I asked you a question. I was kind of confused if you wanted us to do it by looking at the graph or the equation, so I did both. But so
I knew that was going to happen.
So through the equation, you can just look at what value makes the denominator 0, and then through the graph, you can, what did I write? You can look at what x value the graph seems to approach but not touch.
Okay, at x value, the graph seems to approach but not touch. Okay, and we can see this blue line here. And you also made a connection that we're going to refer to later that is very critical. This first sentence, we can determine what value of x makes the denominator 0. So we already advanced because you told me graphically, but you told me first algebraically. In other words, when the denominator is 0, I have a value that makes the function undefined, and in turn, that produces that vertical asymptote. I'm going to look at one more answer. I'm going to look at group 8. The same thing, set the denominator value equal to 0 and solve for x. Although I didn't see here the asymptotes, and the question was, I wanted to see graphically what you saw, but that's okay. Sorry, go ahead. Okay, so, or maybe I'm missing something. No, okay, so I'm gonna go here. Okay, similar. If no equation given, I like this is team 7. Can you read the second sentence for us and tell us a little bit about it? Somebody in group 7, please.
So for this one, I said, if there's no equation, then you can determine it from looking at the graph of where the vertical asymptote is.
Okay. Good. So we're looking at what happens with this graph. It's kind of rising, it's increasing here, and it's kind of, we can see that there's a value that it's getting close to, but then it would disappear, and then it appears here, right? And that kind of gives us the idea of the vertical asymptote. Of course, the first definition is more precise, right? The denominator equal to 0 and solve for x. Good. All right. So now let's talk about the horizontal asymptote. I'm going to go to group 6 and let's see what they said for the horizontal asymptote. Would you like to tell us about it, please? I like the drawings, by the way.
We said that basically if we didn't have an equation, you could just use your like judgment. But if you did have an equation, then we would set each denominator to 0 and then solve for x.
That would work for the vertical asymptote. We're talking about the horizontal now, Emma.
Oh, okay.
In other words, the line, the yellow line that you have there,
Yeah.
that looks very artistic, by the way.
I don't think we had anything for that.
Not yet? Okay. I see here, find the horizontal asymptote and use that number. Okay, all right. Let's see our friends here. Group 5 told me what the horizontal asymptote was, but they really didn't tell me how to determine it. And you know what? Don't worry, because this is relatively new, okay? So this is a bit of a stretch. Here, team 4 tells me where the function doesn't quite touch horizontally. Yeah, so they're doing it visually. I don't know if you want to elaborate here, team 4, please. I like what you did.
I don't know much to elaborate on, just, the lines almost meet it. That's what we went with to describe that.
All right, no, that's good. Okay, good. All right, now let's see here. This is a little bit more interesting. They gave us the y equals -1. Actually, this should be reverse, I think, team 3. The x equals 3 would produce a vertical line. So these two, x equals 3, and y equals -1 are, and I cannot make any changes, so they, oops, let's see, we got kicked out. Let's see if we can come back in. Ish, there it is. Okay, taking a while. Yeah, these two seem to be reversed. Think about it. When x equals 3, that means any point has an x value of 3, which would make a vertical line at 3 that might look something like this. 1, 2, 3, like this. Oh, sorry. Oh my, I'm not helping. It would be a vertical line at 3. Okay, and this y equals -1 would be equivalent to a horizontal line because the y value would be -1. So it would be a line below the x-axis. So watch out because these are reversed. Okay, and then here, yeah, this team gave me the horizontal asymptote as well. And this team very diligently, I can tell Suzanne is here because she likes to write a lot and she's very detailed. So can you comment on this particular one? Anybody from team 1? Suzanne left for the beach, we can see. So one of her partners, there's 2 partners there.
I didn't do this one. I did vertical asymptote, but also like explain it. So it's very similar to the vertical asymptote, but it's just horizontal. So it will like continue, like you'd pretty much just look on the graph. And it's like, it'd be a horizontal line where the function will like never be able to touch. It will, if you were to zoom out of the graph, like it would continue to get closer, but it just can never pass or touch it.
Okay.
Yeah.
That is good. So now let's talk about these for a moment. I'm going to go to one of these that is unused, like this one. Okay. And let's talk about just the horizontal asymptote. Okay. So these equation or this function is something like this. This equation is one linear divided by another. Okay, so something like a y equals mx plus b in the numerator and in the denominator, right? So we have a linear function divided by another linear function. And actually the definition of a rational function is that, right? We take two polynomial functions and divide one by another, okay? So we're going to come back to these next class, but I just want to give you a glimpse. Here's the key idea of vertical asymptote. A lot of you told me correctly, I would take this denominator and make it equal to 0, right? And that would give me the vertical asymptote. When we look at determining the horizontal asymptote, this is the way we think. We look at what happens to the end behaviors of this function, right? So if I were to look at end behaviors of this function, I would get, I'm going to draw this line as best as I can. And I see what happens at the end when x gets very small, when x gets very big, and I can see that this is getting closer and closer and closer to 3 on both sides, right? So my asymptote would be 1 to y equals 3. So that's one approach. But algebraically, if I have the equation, how do I know what it approaches, right? So what we're looking at is the relationship that develops between the leading coefficients, okay? So when we get closer and closer to positive infinity, the value of the x becomes very big, right? So it becomes very big in the numerator and the denominator, yes? So basically what we're saying is when this goes very, very big, this function really becomes something like this. AX divided by CX. Because X is very big, doesn't matter what value we have here, because we're looking at X being close to infinity, whatever we add to infinity is going to be infinity, right? This is a very interesting concept. And basically what we're seeing here is X is approaching infinity here and is approaching it here. And so we're taking A multiplied by a gigantic number divided by C multiplied by the same gigantic number. And guess what? And you probably know these or you have seen these already. These friends kind of cancel each other out because it's the same value. And then we look at these relationship. In other words, the ratio of the A to C on this form. So if my equation was something like this, (3x minus 1 divided by x plus 4, I know my horizontal asymptote, my vertical asymptote is going to be at -4. My vertical asymptote is going to be the relationship between the coefficients of the x. In other words, is going to be 3 divided by 1, or 3. And that will give me the equation of the horizontal asymptote. Y equals 3. Okay, and that was new. So some of you knew that already. For some of you, this is newish, but that's where it comes from. If you can understand this disaster that I just made. Okay, cool. So now let's go to the domain, and let's begin with Team 10. Team 10, tell us about the domain. How do we figure the domain?
Okay, so Kate did this one, but her microphone's not working. So basically for the domain, you kind of just look at the you can use the vertical asymptote. So if we're looking at this graph, you can just use what the vertical asymptote is, and you know that that value is a restriction in the domain because that is the x value that it cannot equal to. So in this graph, it can be any number except for that value.
I
If that
think
makes any sense.
if it's even if it's silent, I think that deserves a big clap. So at the count of 3, everybody, I can see some of you give me a big clap, even if it's silent. 1, 2, 3. Right. Well done, Malvi. We're not going to go to anybody else because that explanation was just perfect, right? That's the connection. The domain, we look at the vertical asymptote. Fantastic. So now let's go to Team 9 and tell us about the range.
So for the range, we said that it depends on horizontal asymptotes. So you find the value of the horizontal asymptote, and that value is what the range can't be. And so y is just have all real numbers except for that one value.
And anybody in Karen's team, our partner, want to elaborate a bit? I don't know if the sound was a bit choppy for everybody. It was a bit choppy for me. No, that was very good, Karen. Basically, Karen, we see these functions are interesting because there's some symmetries in them, isn't there? So when we look at the domain, we look at the vertical asymptote. When we look at the range, we look at the horizontal asymptote. And those are the values that are forbidden for our function, for f of x, for the range, and for x for the domain. Very cool. Okay, we're going to keep going. So now Team 8, tell us about how we find the x-intercept. Well, I think you told us here in your note, but can you elaborate a bit?
So it's basically just where the function intercepts with the x-axis. So the point would be like 0.5 and 0, or a half and 0.
Okay. Thank you, Maya. Yeah, where the x-intercept, graphically, we can see it here, right? Where the function crosses the x-axis. And let's make the connection now to the algebraic part. And when I say the algebraic part, I want you to think that we do not see the function, that what we have is just the equation, right? So look at what Maya wrote here, 0.5, 0. The x value is 0.5, but the f of x is 0. Let's see what our Team 7 said about the x-intercept. We're having trouble with digital posts. Team 7, can you tell us a little bit about these, please?
Yeah, Mr. Garcia, I kind of came to the same conclusion. But I guess algebraically, if it when the x value becomes negative, going from a positive number, that's when you would find the x-intercept.
Okay.
Or sorry, goes from a negative f of x to a positive.
Well, ish. It actually is when it's 0. So the x-intercept happens when f of x equals 0, right? And that's why I was trying to highlight on Maya's answer. Let's see if somebody else put it as an ordered pair. Here, right? 0, actually, this would be 0.5, 0. So this ordered pair is reversed on Team 3, right? Is this value. Okay, So the key point here is this, relatively simple. We find algebraically the x-intercept when the function equals 0. When f of x is 0, then that's our x-intercept. What about the y-intercept? Let's go to team 2. Tell us about the y-intercept. Go ahead, please. Or the y-intercept you found. No? Anybody there? We lost our team 2 friends? Not sure. Who do we have team 2? Marcus. Oh, Madia sometimes has trouble with her sound. And I think Marcus as well. Okay. So I'm going to comment on these very quickly. The y-intercept. The y-intercept, well, is where the function crosses the y-axis. And if the x-intercept is found when the function or y is 0, the y-intercept is found when x is 0. So we're looking for the y-intercept to be this point, right? And the order pair is not 0, oh yeah, it's 0, but it's comma -2, right? -2. And that would be our order pair. So y-intercept when x is 0, x-intercept when y is 0. And that we've seen before in other courses. Okay, now let's just tackle the last 2 bits. The positive and negative intervals, and we go again to team 1. Last time it was Amber. I know it's Amber, Suzanne, and Keisha. So either Suzanne or Keisha, would you like to tell us about your answer here, please?
Keisha can do it.
I don't see Keisha, you know, but that's me. I don't.
Okay, then.
Go ahead, Suzanne. I don't know.
So for a positive and negative interval, a positive interval that occurs where the function lies above the x-axis, so where you have positive y values, and it's a negative interval if for the portion where it lies below the x-axis.
So can you tell us in this specific case what intervals would be, in which intervals, excuse me, I'm not phrasing my question correctly. In which interval or intervals is this function positive?
Okay, so I would, the positive interval, let's see, you've got that left-hand wing, the upper left branch of the function. So that is x values from, what's that, -1 or so to -infinity, not including -1.
Okay, so let me paraphrase what you just said.
So that's a positive.
So
that's
it would be from -infinity to -1.
Yeah, but not including, well, but not including the -1.
It's an open interval. I hope you can read that this is the infinite symbol and not a pair of glasses. Okay, yeah. So that's one interval. Is there another one?
You have another positive interval from, it looks like approximately 1 up to +infinity.
Yeah, this was kind of the x-intercept, which it's 1/2. Mm-hmm. So this interval would be, actually it's open because at 1/2 the function is 0, right? So it's not positive. Okay. So let's say it would be 1/2 all the way to +infinity. Yeah, so those are my positive intervals. Sorry, I did this wrongly because it may appear that this is a negative interval, but it's not. This is an interval where the function is positive, these 2 intervals, right?
Mm-hmm. Yeah.
And then what would be the interval where the function is negative?
So that's where it's below the x-axis. So that is from about -1 up to a half, not including the -1, not including the half.
All right. So it will go basically the interval that is not included here. So from -1 to 1/2. And it is an open interval, right?
Yeah.
It doesn't touch the -1 because it's the vertical asymptote. It doesn't touch the 1/2 because at 1/2 the function is 0, and we're looking at being negative. So nice. So these are interesting, and thank you for the very clear and thorough explanation, Suzanne. Cool. And then now let's go back here. Let's see who had intervals of increase and decrease. I was looking for something specific. Team 3, would you like to comment on what you wrote here? I think this is our team with the sound issues.
No, I'm here.
Oh, sorry, my bad.
So on the assumption I didn't screw up my x and y values and swap them again.
That's okay, don't worry.
We tried as hard as we possibly could to write it out and to visually explain it. So it's literally exactly as it says. If you have something that's increasing, you're gonna watch it go up the x-axis and down the y. So it's gonna be like going down, and then decreasing would be the way up, right? So I'm having a hard time to break this down. We literally just tried to visually paint an image of what direction the graph would be going in, or the function, I'm sorry.
Yeah. Okay, cool. So let's talk about this. Let's look at this function here. What's happening in this section? Is that increasing? Give me a thumbs up if you think the function is increasing there. Yeah, can you give it to me in on the reactions at the bottom? I see Karen, I see Malvi, James, Jonathan, I see Nolua. Okay, it's increasing, right? And what about here? Give me a thumbs up if you think on this second interval the function is decreasing. Okay, good job. Yeah, this function is always increasing, except at the vertical asymptote. And Stephen, maybe I'm paraphrasing what you're just trying to explain. I'm looking at what happens graphically, and I can see that this is getting bigger, to make a long story short, right? The y values are increasing here from one point to the next, and similarly here. The function is always increasing. We would write these as intervals using interval notation, since we just learned about it and we think we're all that. And the way we would write the intervals of increase and decrease would be something like this. The function is always increasing, right? So we can do it in a variety of ways. We can say the function from -infinity to +infinity, but not excluding -1. Or we can break it down more to make it more mathematically correct, I think. We could break it down and say from a -infinity I'm having such trouble with infinity thing, to -1, and sometimes we put, like in set notation, the union. I don't want to confuse people. And from -1 to +infinity, right? Kind of two intervals, just showing that everything except the -1. Okay, so we made a lot of connections with these function. We basically did the anatomy of these function. I hope that these analyses helped some of you. There's still some misconceptions that I see. Hopefully this was helpful. And of course, the Jamboard stays there, and you can go and refer to it. I'm going to see if I can make some of these ugly numbers pretty. But the Jamboard is there.